Alright, let's look at the definition of area. Alright, before we get to the actual definition of area, we would like to look at its motivation. Alright, so I'm going to use the GeoGebra to do some demonstration. Alright, let's say you have a function x cubed. So graph is given here. Alright, then area under the graph of y equals x cubed from 0 to 2 is this shaded area here, right? And the area is actually exactly equal to 4, right? Then we're going to look at the right sum, right? With right sum, R1, when n equals 1, right sum gives you 16, right? What we're going to do is I'm going to increase the value of n by using this slider, right? So actually maybe let's do it a little bit more gradually, right? So this was 1, right? Then 2, right? Look at the right sum. Right sum R2 is going to be 9, so it's going to be a little closer. And 7.111 when n equals 3, R4, R5, and you keep on doing R10, R12, and you can see that the approximation using a right sum is getting closer to the actual area 4. So you can see that I'm using a lot of rectangles, and after a while you can even see the rectangle. It's all solid, right? But you can see that if you look at the Rn, this value is getting closer to 4. Right now it's 4.011 4.01 right now, and if you use let's say n to be 1000, it actually goes to 4.008. so error is only 0.008, right? So as you can see that as you increase the number of approximating rectangles, the error is going to be very small, so the right sum is going to get closer to the actual area. Alright, so using that as a motivation, let's try to define the definition of area. So the bigger the n is, the better the approximation is. So that's how it is. Alright, so here's the definition of area. First, I'm going to have to do kind of a general notation. So you have a region from A to B under the graph of function f. So this is the graph of function f. Right? So we are talking about the region under the curve going from A to B. So we're talking about this shaded region. Right? So what we're going to do is we're going to split the interval from A to B into n equal subintervals, right? So I'm going to put a bunch of tick marks, right? Right? So right? So first number, A is exactly the same as x0. Next one is x1, x2, and so on. And the last one is going to be there n of them, so it's going to be xn. Alright, and we can compute delta x. So delta x is simply, so this is the width of each rectangle. So the length from A to B would be, of course, B minus A. We split that into n equal pieces. So this is a formula to find delta x. Alright, so if you want to find the right sum, so I'm going to call it R sub n because there are n approximating rectangles. Alright, so you can see that the first rectangle, because this is a right sum, so I'm going to use the right endpoint and then determine the rectangle here. Right? So you can see that the height of the first rectangle is determined by f of x1. Right? So we have, I'm going to put f of x1. Alright, then the width is delta x. So I'm going to leave delta x as it is. So it's going to be multiplied by delta x. So that's going to give us the area of the first approximating rectangle. Alright, so the second one, use the right endpoint, which is at x2. Then determine the height using using that. So this is going to have the area, the height, it's going to be f of x2. So I'm going to add f of x2 times the width is again delta x. All right, so you keep on doing that. So I'm going to say dot 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 so that we don't have too many. So we're going to keep on adding those approximating rectangles. All right, the last one is the nth rectangle. So this is going to be xn minus 1. Then we're using the right endpoint, so we're going to use this guy to determine the height, which is at xn. So last approximating rectangle has the height of f of xn. All right, so this is kind of a general notation for right sum. All right. And math people are pretty lazy, so what they do is they can even get a shorthanded notation for the same thing. All right, so you can see that the sum is going from x1 through xn. So I'm going to use the summation sign, so the sigma notation, so summation sign. All right, then you have, so the form is all of them has f of xi, I being the index. And the index goes from 1 to n. So we say I is going to start from 1 and I is going to end at n. Right? Then you have delta x. Right? So this is the shorthand notation for right sum. Right? Then we can define area by doing this. Remember that the bigger the n is, the better the approximation. So bigger the better, which means I'm going to send n to positive infinity, right? So that's the best we can do, right? So the definition is area A is going to be simply, I'm going to make n go to positive infinity of right sum n, right? And which is limit as n approaches infinity. Right sum is a summation. I goes from 1 to n. Then you have f of xi and the delta x. Right? It is actually really doesn't matter if you use the right sum or left sum or even a midpoint sum. The limit is going to go to exactly the same because you make the approximating rectangle very, very skinny. So it really doesn't matter which point to use to determine the height of each rectangle. So this is actually, you can think of it, we tend to use right sum because the formula looks cleaner, but you can do a limit of left sum. And you can take the limit of the midpoint sum, so I'm going to call it mn, right? They are going to be exactly the same, right? But the definition of the area is this guy right here. Right? That's it. I hope that this was clear.